for the Monday after a holiday. Okay, I hope you had a great weekend. We are down now officially to 6 class meetings before our final exam week, so I'm sure that's a relief to you. And I believe we have 1 test in there, right? What's that? Next, right? It's next Wednesday? Am I reading this right? Yeah. Next Wednesday is our next test, all right? So technically we only have 5 more lectures. So we got some work to do. We're a little bit behind on the calendar, and I'm not real concerned about that, all right? So let's see if we are recording microphone. Okay. So in college algebra, we traditionally cover 5 different types of functions. And well, let's see, how many do I have listed here? 3, 4, 5. I have 6 listed. So why did I put 5 types of functions? They are covered together, but they are very different functions. Okay, so, but you're kind of on the right track. It's not these 2 that are together. It's these 2. So those are actually both in the category of polynomials. In fact, you could argue that a line is a polynomial also, but lines are very different than parabolas and polynomials. These 2 right here that we've been looking at, this was last class, right? We sketched those, and those looked curved, and we had the end behavior and all that stuff, right? Well, parabolas are also curved, and they also have the same end behavior as these do. These are straight lines, so that's why I break these up. We've got lines, we've got polynomials, and then we still have 3 to talk about here. Rational functions, exponential functions, and logarithmic functions. But I thought today by starting, I would just kind of remind us what we've done. Hopefully we all are comfortable graphing lines. Parabolas, we could find the vertex, and we could find a lot of information about a parabola, right? X-intercepts, highest point, all that stuff. But with these guys, these polynomials, we were only able to find the x-intercepts, whether or not we bounced or crossed, and the end behavior. Does this all sound familiar? Okay, so lines come up in the real world. I can make a very simple example. Does anybody here have a job where you get paid hourly? Okay, your pay is a linear function, right? If you were to graph the hours you work and the money you make, if you work 0 hours, you get 0 pay, right? You work 1 hour, then you make your whatever it is, what, $3? What? It feels like it's $3, doesn't it? Sometimes. Whatever it is, right? Let's just say you make $12 an hour, okay? Who cares? Then you work 2, you're up 24, so that's a line, right? So linear functions are good at modeling certain things in the real world, right? Parabolas, one of the things parabolas were good at was objects that were traveling through the air, right? How about polynomials? Think of anything in the real world that might go like this. What's that? The economy. Income, for a business, functions that behave that way. You look at the stock market, does certain things, right? So polynomials are good at modeling certain situations. But in the real world, we need more functions to model the things that happen around us. And rational functions are a very special category that we're going to talk about today. So I thought I would start off by motivating the idea of a rational function. With a little quiz. Not a quiz, this is not a quiz. Hey, it's just, I'm going to ask a question. Okay, so we're going to start with rational functions. So that's what we're studying today. So everyone understand, we are no longer talking about polynomials. So that whole left end, right end behavior, all that stuff, and all the bouncing, crossing is no longer applicable. All right, we are in a new category of functions. So here's my little brain teaser. This is a quote from a movie. I'm going to see if anyone knows the movie. All right? And I may mess the quote up just a little bit. On a long enough timeline, this is the quote, on a long enough timeline, the survival rate for everything drops to 0. I didn't think anyone would know it.
Did you just date yourself with that movie?
Pardon?
Did you just date yourself with that quote?
Yeah, I think I probably did, yes. Yes, I'm sure I did. But it's one of those weird movies that has survived time. I'll give you the quote one more time, then I'll give you the main actor. Okay? On a long enough timeline, the survival rate for everything drops to 0. Okay. Brad Pitt?
Is that like One for the Money or Moneyball?
No. That's a good guess because that's the baseball movie, and it is very analytical, and they get into statistics and stuff. No.
Newer movie of his? Like, how old are we talking?
Pretty old, I think. I'm not sure now. I don't know, man. Okay, Ed Norton Jr. is in the movie also.
Is it Fight Club?
Fight Club. How many of you have never seen Fight Club? Never seen Fight Club.
We can't talk about it.
I know, that's... Oh, you can't. Okay, so, all right. So in that movie, it's a crazy movie if you ever watch it, but there's some really deep ideas in that movie. And one, this whole thing, this quote has nothing, I think, to do with, well, maybe it does. The quote does. The quote is saying this: on a long enough timeline, so let's say this is time, right? If I bring this timeline out on a long enough timeline, so if this timeline goes on and on and on, if it's long enough, the survival rate for everything drops to 0. So let's just take, for example, let's talk about something like a light bulb, all right? Let's assume you go to the store, you buy a new light bulb, you put it in the lamp, whatever, you turn it on, it comes on, all right? So at time equals 0, let's say that's time 0 when you bring it to your house, this is going to be the probability that it works, okay? The probability that it's working. In other words, that it's alive, that it functions, right? So at 0, it's up here at 1. 1 is the same as 100%. Agreed? If I say take 1 and turn it into a percentage, you would move the decimal point over 2 places, and it would be 100%. So you turn it on, you see it come on, at time 0, 100% it's working, right? Okay, on a long enough timeline, the survival rate for everything drops to 0, which means that if I come down here 1 day later, let's say these are days, 1 day later, what do you think the probability is when I walk in that room the next day and I flip the light switch on that it comes on? Would you say it's a very high probability or a low probability? Pretty high, right? Maybe in the 90s, 99 maybe, 99.5, whatever. It's pretty high, yes? Okay, so let's now continue to move down this timeline. If I go out, this is not going to be drawn to scale, but let's say I go out 365 days later. I hope it works, right? But are you 99% anymore, you think? No? So now it's dropping down, yes?
I think that depends on what.
Depends on a lot of things, right? I mean, there are a lot of factors involved here, but would we agree that it's tending this way? Yes? And what if I go out to, let's say, 1,000 days? So now you're what? About 3 years in? Yes? Probability that we flip the switch on, it works, is now pretty low, right? It's getting lower. These LEDs last a long time, but okay, so let me go crazy here. And let's change this. Well, let's not change it. Let's just go further out on the timeline, but again, it's not drawn to scale. What if I go out to 100,000 days? Wait, I know that's a crazy idea. How many days, how many years is that? What's 100,000 divided by 365? Someone do that for me real quick. So we're measuring this in days. So what was it? 100,000 divided by 365. 273 years? What do y'all think? So assuming the building's still there, that you're still alive, and someone's there to flip the switch, okay? What do you think?
Has it been used every day?
Maybe, maybe not. This is a probability, okay? We're talking about probabilities here. Do you think the probability is, what do y'all think the probability is? 0. Do you think it's 0?
I'd say it's
Can you say that though?
very
with 100% certainty, can you say that 200 something years later that light bulb will not come on? You can say it with certainty? Okay, let me challenge your idea.
What if it's being used like how you're saying it's being used as well? But not if like you never use it.
Okay, so what if I used it every day for all the way up to 100,000 days later? Guaranteed? So at what point then, let me ask you, at what point would it have still worked? Yeah, see what I'm saying? Like mathematically, like at what point are you going to say it's zero? Because you can't tell me when it's zero. You can only tell me it's zero when you actually flip it and it's dead, right? But we're talking about probabilities here. So I'm going to say that it's like really small, like infinitesimally small. What I mean by that is like, what's the probability that you're going to win the lottery? Pretty small? Okay, how about this idea? The probability of winning the lottery every day for the rest of your life. What's that? Zero or no? It's not zero. If you play the lottery every day, right? Let's just say you did. Do you have an odds of winning? You do. Could you win every single day for the rest of your life? Could it happen? Yes. Will it? Probably not. But you can't say zero. You cannot say zero. We're talking about a number that's infinitesimally small. We're talking like 0.0000000000000000000000001 maybe, right? Just like it's like being struck by lightning every day and living, you know, like that. Those odds are just infinitesimally small, but not zero. Am I kind of selling you on this a little bit? So what we have here, if you look at this, and I want to connect these dots. This looks too much like a line. What we have is something that looks more like this. Okay, and what's happening out here is that, like, here's my x-axis. This graph is getting closer and closer and closer, but never actually ever getting to zero. Does that make sense? Kind of? So this is not a line, right? This does not look like a line, right? So we can't use a line to model this behavior. Can we use a parabola? Well, this doesn't look like a parabola. Parabolas are like U's that open up or down, right? Can we use a polynomial? No, because polynomials do this at the ends, it does this, right? It would be nice if we had a function in mathematics that would model this sort of behavior, right? Because it happens out there. I mean, you could replace the light bulb with a human being. What's the probability that a human lives 365 days? Just on average, you know, on average. Pretty high, okay? But on a long enough timeline, that probability drops to zero. Now, what are the odds? What are the odds? Let's change this to years. Let's go with a human being, okay? Person. What's the probability that you make it to your 30s? Pretty good? I mean, if you're living in the United States of America, I guess, you know, you're better off than some places, worse off than others. I would say probability from the beginning, you know, I think in the beginning it actually probably drops a little bit because there's a lot of things that can happen when you're young, but, you know, whatever. And then it starts to go down, right? Okay, what do you think, when do you think it starts to get kind of, getting, what, 60? Oh, shit. Okay, 60 we're already small? All right. What about 90? Think you make it to 90? Pretty small, right? Depends on if you're a man or a woman also, right? Yeah. Women get stuck here on this planet longer than us. I don't look at that as an advantage. Okay, 90. 120?
It's happened.
Has it happened? So you can't say zero, right? All right, let's just go out. Let's just say like 200 then.
No, zero.
I don't know. Can we say zero? I don't think we can say zero. Just because something has never happened doesn't mean it can't happen, right? Right? Now, we're talking, now I agree, I don't think it's going to happen, but what do you think's more likely? A person living to 200 or a person, again, winning the lottery every day for the rest of their lives? Like, they both aren't going to happen, right? But you can't assign a probability of zero to it Because as soon as you say 0, then you have to tell me what age is that 0 point going to happen. Like you tell me absolutely no chance that they can live to 121? 122? Like where do you put the 0? You can't. So what we do is, the probability just drops down to something so insignificant. This is also the way, think about medication in your body. When you take medication, what happens? Initially, you have a high concentration in your bloodstream, and then what happens over time? Starts to decrease, right? Starts to go away, go away, go away, go away, right? And at some point, it's not even measurable. You can't even get the measurement of it anymore. Does that make sense? 160? 16. Okay. So is 120 then you think reachable? Maybe? So you can't say 0. But okay, do you get the idea? The whole idea here is that we do not have a function yet that will do this, right? We don't. I guess that quote, on a long enough timeline, the survival rate for everything drops to 0 is just basically saying we're all going to die, right? At some point we're all going to die. Everything's going to die. Cheery, huh? Yeah, what a great way to start Monday. We're all going to die. Let's move on. Okay, so what is a rational function? Well, the rational function is going to be able to draw what we just did. And the key to this is that word right there, ratio. So rational function is a ratio, and when you think ratio, think fraction. So I'm going to write down the definition of a rational function. Rational function is a function that looks like this. It's a polynomial divided by another polynomial. Now we've studied polynomials, haven't we? We just did polynomials, didn't we? And we said that parabolas are polynomials, aren't they? And we also said that lines are polynomials. So basically, take any function that we've ever studied in our lives, like up to this point, and just make a fraction out of them, and you will create what's called a rational function. The big problem with rational functions is that they do not all look the same. You know how like all lines kind of look the same? And all parabolas kind of either go like this or go the other way? And all polynomials kind of look the same? Rational functions can look very different. They all have certain things in common, but if I give you a rational function, you a rational function, you graph them, they can look very, very different. So these are very challenging functions. And we are not going to go through a full-blown treatment of these. We're just going to just kind of chip at just the surface of them and just look at just a few kinds of rational functions. So the first one I want us to look at, your first example, is this one right here. F of x equals 4 over 2 plus x. That is an example of a rational function. So let's try and get an idea of what in the world this thing is doing. So what we're going to do to kind of get our minds around this is we're going to first talk about what's called the domain of this. And I know we have stayed away from domains and ranges quite a bit up to this point, and that's because polynomials haven't really had any problems with domain, but this is the first function that we've had where we actually do have a problem. There is a certain value of x that you can't plug in. Can you all tell me what x I could not plug into this thing? Is there anything that I would try and plug in for x, and when I did it, something really bad would happen?
0.
Okay, if I replace that with 0, you're on the right track. I don't care if that's 0. I just don't want this to be 0, right? So what would you have to plug in there that would make that 0? Negative 2. Do y'all agree with that? So let me look at this. I know right now x cannot be negative 2. Because if x is negative 2, I get division by 0. Y'all follow that? Yes? Yes? Okay. So right away, here's what I can tell you. If I were to start to graph this, if I went to -2, like there's no graph here. There's no graph at -2. I'm not allowed to plug -2 in. So you know how when we draw a line, we don't ever have to pick up our pencil? When we draw a parabola, we don't have to pick up our pencil? When we draw a polynomial function, we can just draw it without picking up our pencil? When we go to draw this, if there's a picture over here of I'm drawing it, when I get to -2, I'm going to have to actually pick my pencil up and go to the other side and continue drawing, because at -2, I'm not allowed to put anything. Does that make sense? So I already have something very different than I've had in the past, right? Okay, so let's try and figure out what this is doing. And I think the way that we're going to do this is we're going to make a t-table. This is going like old school now. We're going to make a t-table. We're going to do x here, and we're going to do f of x here. So we're going to just start picking some points and plugging it in, and then we're going to draw some dots and see if we can connect the dots to see what's happening. So let's just start picking some points. How about 0, right? Let's just plug in 0. What happens if we plug 0 into the function? So what happens if I put 0 here? 4 over 2, which is 2, right? We get 2 out. So that gives us 4 over 2, which gives us 2. So look, if I come over here to the graph, and I think I'll do the graph in a different color. I'll do it in blue. This is the point 0, 2, right? You plug in 0 for x, you get 2 out. So if I go graph this, 0, 2 means that point right there is on my graph. Agreed? Let's see if we can get a few more. I don't want to plug 1 in. Do you see why I don't feel like plugging 1 in? If I do 1, I'm going to get 4/3, and that's a decimal. So I'm going to try and avoid that. I'm going to plug in 2 instead. Because if I plug in 2, what is it going to spit out?
1.
You get 4 over 2 plus 2 is 4, so this is going to spit out 1. So that means at 2, I'm at 1, right? Okay, so if I go graph that, if I'm at 2, here's 1, here's 2. At 2, I'm at 1, so there's my point. Now, this next part is the critical part. I want you to pay attention to what would happen if I continue to let my timeline get bigger. Okay, so imagine I keep going out here. So what if I were to put a 10 here? What would I have got there?
3.
I would get 4 on top, and then what's on the bottom? 2 plus 10 is 12, right? Yes?
Yes.
And this number is like 1/3. That's a small number. I mean, 1/3, right? So I could plot that point, couldn't I? But what happens if I let this number get bigger? Like, what if it's 100? That'd be 4 over 102, right? Because I put 100 plus 2. And that number is even smaller, right? Really small. Yes? Small? What if I go out to 1,000? What am I going to have? 4 over 1,002, which is even smaller, right? Are y'all following me or no? Yeah. So as I go out this direction, these numbers are getting smaller, just like the probability of a light bulb working, right? It's going to do exactly what I wanted it to do. Now, what if I go out to 1 billion? I'm going to get 4 over 1,000,002,000, which if you did that on your calculator, you would still get a number that's a little bit bigger than 0. So you still have numbers no matter how far you go. So my graph to the right looks like this. Right? It's starting to flatten out towards 0. So the way we do that is we draw a dotted line out the edge like that along the x-axis that lets everyone know that we realize that this is approaching, it's getting closer, but it's never actually going to touch. All right? It's just going to get closer and closer and closer. This right here is known, or we will call it, a horizontal, because it's this way, and then this is a weird word in mathematics. Asymptote. Horizontal asymptote. It's like the P is silent. It's a weird word. Asymptote. 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 Tote. It's weird. Just say it real fast. No one will care. Okay. Horizontal asymptote. So horizontal asymptote, the way I want you to visualize or think about a horizontal asymptote in this class is almost think of it like a magnet. And it's kind of like pulling your graph towards it, right? But your graph never actually gets to it. Make sense? Any questions? All right. That's what happens out this way. So it's doing what I want it to do. But what happens if I start going this way? Does it get big? Let's check. Yeah, I mean, that's a good guess. I mean, it seems like maybe it might do that, right? Let's see what happens. So what I'm going to do is I'm going to clear this out, and let's pick some other values. I'd like to get a, I can't plug in -2, right? I'm not allowed to do that. So I'm kind of curious what happens right here, like in between here. So what's a number I could pick right here? Somewhere in here. -1, right? Let me try -1. What would happen if I plug -1 in here? I get 4 over 2 plus -1, right? And 2 plus -1 would give me just 1 down here. So this is just 4, isn't it? So at -1, I'd be up at 4, which is kind of promising that we go to -1, we're up 1, 2, 3, 4. It's kind of promising this idea that it might be going up. Y'all with me? I cannot plug in -2. So somebody with a calculator right now, I want you to do this for me. First, somebody please give me a number that's really close to -2 right there. -1.9. Y'all agree that's pretty close to -2? So somebody on their calculator do 4 divided by 2 plus -1.99 and tell me what they get. I'll double check. Or if you don't feel like doing the work, I'll do it. But if you do it, I'll give you a 1,000-point bonus. No. Yeah. I'm kidding about the 1,000-point bonus. Are you withdrawing? What do you got? What'd you get?
It's negative 2.10.
You got negative? Did you get negative? Is that what you said?
Yeah.
Got to see how you type that in. Did you type it all in at one time?
Oh, no.
No. You should be getting a big number. There you go. That's more like it. 40. So make sure you're using parentheses properly when you type this in. You should be getting 40 here. So, whoa, what just happened? Like we tried to get close to -2, right? We tried to get close to it, and where were we? Way up there, right? Way up there at 40, outside the room, outside the building, all right? So we're way up there. Okay, let's try and get even closer. Can you give me a number that's even closer to -2? Not 1.9, but how about 1.999? That's even closer, right? We can do this all day long. Try that in the calculator, see what you get. Anyone got it? Who's got it for me? No one, huh? 4,000. Did I put too many 9s on this one? Look on this one, I put too many 9s there to get 40, sorry. 4 over 2 plus -1.999 should give you 4,000. Something very crazy is happening. As we get really close to -2, right? As we try and draw our graph this way, what's happening to our graph? It's going up, and it's going up very rapidly, right? So this behavior, we have not seen that behavior. It may appear to you that we have. Like you might think, oh, that's just like a parabola. It just goes up on the left. But the difference is there's a barrier that we can't cross. Like we have to keep going up, but we have to always stay to the right side of this dotted line. So this -2 creates this barrier that we can't touch. And that barrier has a name. What do you think we call it? A vertical asymptote. So this is a horizontal asymptote. This is a vertical asymptote. Now, we could then go and start picking some values on this side. Right? So we could like take -3, plug it in, -4, plug it in, and figure out what this graph is doing. I'm just going to draw it for you. I don't want to go through all the work, okay? But what you would get is this on this side. Your graph would go down like this, and then over here, guess what it's going to do? It's going to go back and start getting closer to 0 on this side. So if you start taking some values and plugging them in here, you would get that picture. So look at, just take a step back and you know, take a look at that. That is very different than anything we've seen, right? Very different. But it's great at modeling certain things, because we've got this dipping down that, you know, asymptotically approaches something. And that can be useful to us, all right? So the question now is, if I give you a rational function, if I give you one, can you identify where the horizontal asymptote is and the vertical asymptote? That's what we're interested in figuring out here, all right? And that's pretty much all we're going to do in this class. I mean, I'm not gonna have you graph these by hand. It takes forever. It's a long, tedious process. I'm more interested in, can you find the horizontal and vertical asymptotes? That's it, all right? So y'all ready to do that? Y'all look really thrilled today, I'm telling you. Yeah, yeah. Why work? Hey, that's not my doing. I was born into this too. All right. I would like to look at this one. Find vertical asymptote. From now on, I'm going to abbreviate it VA, because you'll get tired of writing it and I get tired of writing it, okay? Find the vertical asymptote and then find the horizontal asymptote. Can I just put HA, you know what I'm talking about, or no? Want me to write it out? Okay. All right, vertical asymptotes are the easiest of the two to find. Okay, all you have to do to find the vertical asymptotes is set the denominator to 0. Because anytime this bottom piece is 0, we have this undefined point, like in the previous problem where we had that, it was happening at -2, right? And what happened was our function was doing something crazy on both sides. So we just want to know when the bottom is 0. So we set this equal to 0, and we solve and we get 2. Okay? That pretty straightforward? There's not a lot of magic happening there? Now, visually, here's what we're saying. Is that 2, our graph is going to go like this, like that. Or it could go the other way. It could go up on this side, down on this side. It could also go up both ways or down both ways. But the main idea is that when we get here, our graph's got to do something. It can't go through that line. I almost look at it like a brick wall. You're driving down the road, and it's like you have to turn away from the brick wall. You can't go straight into it. So this is how our function behaves at vertical asymptotes. We good? Okay, so we've identified it. It happens at x equals 2. And How about the horizontal? Horizontal is much more challenging to get. All right, so you ready for me to explain how to get it? For the horizontal, asymptote, what you're going to do is compare the degree of the numerator to the degree of the denominator. What am I talking about? Yeah, numerator is the top function, right? The denominator is the bottom, right? So that's what we did here. We said denominator 0. To find out where our graph flattens out at the edges, we have to compare the degrees. So look at the numerator. Can anyone tell me what the degree of this numerator is? 1. That's the highest power of x, right? 1. What's the degree of the denominator? 1 also, okay? We want to look at those two numbers and compare them. And we have 3 possible things that can happen now. These numbers are either the same, right? Which in this case they are. These numbers are the same. This number on top is bigger than that one, or this number on top is smaller, right? Do you agree there's only 3 possibilities? They're either the same numbers, top's bigger than the bottom, or the top smaller than the bottom, right? So here are the 3 different scenarios. First, if the top is bigger than the bottom, you have no horizontal asymptotes. So that would be nice. If this happens, like if this was x squared up here, x squared plus 4, you would have no horizontal asymptotes. So you would have, that's like the light bulb thing, that would not be happening. Okay, it would not flatten out. If the top is less than the bottom, then the x-axis is the horizontal asymptote. And then the third possibility, I'm going to leave this up here. The third possibility is if they're the same, and I think this is the hardest one right here. If they're the same, then what you have to do is take the leading coefficient of the top and divide it by the leading coefficient of the bottom. Divide them. Okay, so let me try and clarify all this. Those are the steps to find your horizontal asymptote. You're going to have one of these 3 things are going to happen. So let's take a look at ours. Which case do we have here? Do we have case 1, case 2, or case 3? We have case 3, right? These are the same. The degrees are the same. In this case, we're supposed to take the leading coefficient. I should probably tell you that means leading coefficient. We've already talked about leading coefficients, though. What is the leading coefficient of the top one? 1, right? What's the leading coefficient of the bottom one? 1. I'm supposed to create a fraction out of those. 1 over 1. 1 over 1 is 1. This is my horizontal asymptote, which means that if I come over to my graph, I'm going to erase all this. If I come over to my graph, here's what I can tell you about my graph. We had a vertical asymptote where? 2. And we have a horizontal asymptote where? 1. So 1 is, like let's say right there, there's 1. Did y'all see that? 2, vertical asymptote, horizontal asymptote is moved up 1. So if I draw this graph, what's going to happen is as I draw it towards here, it's going to have to do something like that. But as I draw it out to the edges, it's going to have to get pulled towards that magnetic line that kind of gravitates towards that line. Does that make sense? You sure? Okay. So this is where in a real college algebra class where you get into the details of this, we'd have to figure out how to fill in the missing pieces. All right? Like how do we draw this. And it would turn out, let me look at it real quick. It would turn out looking like -4. This graph actually looks like this. You don't have to do this, okay? Whoa, wait a minute, hold on. 0, yeah, -2. That's what that graph looks like, all right? I'm not asking you to do that. All I want you to do is identify this and this, all right? Filling all this in is just, it's too much for what we're here for, okay? But that's what would happen. You all right with that? Okay. Let's do another one. Let me give you another problem where you identify the vertical and horizontal asymptotes. And then I'll show you the graph, but again, we're not going to have to go get those. So how about this one? Find vertical asymptotes, find horizontal asymptotes. So first step, vertical asymptote, we set the what? What to 0? Denominator, right? So to find the vertical asymptotes, I said x squared minus 9 equal to 0. And then you look at that, and hopefully you recognize it, right? That's difference of squares. X plus 3, x minus 3. Factor, right? And then you set each of those equal to 0. So you get 2 answers. -3 and 3. You could have also moved the 9 over and took the square root on both sides. You could do it both ways. Just remember plus and minus. Okay, don't forget the plus or minus. All right, so look, here's what we're saying. If we were to graph this rational function, I would have a vertical asymptote at 3 and at -3. So I have these two barriers that when my function gets close to these, my function has to like freak out and do something, right? Okay, how about horizontal asymptote? You need to compare what? The degrees. What's the degree of the numerator? 1. What's the degree of the denominator? 2. Okay. So what case are we in here? I gave you 3 cases, case 1, 2, and 3. Which case are we in? 2, the second case, right? The second case was when the top was smaller than the bottom, which is what we have here. And what is your horizontal asymptote when that happens? The x-axis. The x-axis. So here, you know, the top is smaller than the bottom, which means the x-axis. So here's how I'm going to draw that over here on my graph. I'm going to, on the edge here, let me just erase a little of this. I'm put a dotted line here, and on this edge, a dotted line there. Notice I'm not drawing my dotted line all the way through, okay? It's just at the edges. That's all you do for this horizontal asymptote, right? So that's what we would need to start the graph if we were, you know, asked to graph this thing. This is all I want you to be able to do. Does that seem okay? Now, do you care to know what it looks like? I could probably fill it in pretty quick here. So it actually looks like this. It goes like this here. Let me just double check something. I've got an x-intercept here. 1, that's negative, so it goes down like this, and then here it goes up like that, and then on this side, yeah, it should go like this. That's what that graph looks like. So it's like as it goes this way, it gets closer and closer to 0. As it goes this way, it's like, oh shit, there's a wall, and it goes like that. And then on this side, it's like, okay? That's the graph. So different than a line, a parabola, or a polynomial. It's so different, right? All right. How would this problem change if I gave you this instead? I'm going to leave everything except I'm going to make that x cubed. would your vertical asymptotes change? Would your vertical asymptotes change? Sure? What's the step to find the vertical asymptotes? Set the bottom to 0, right? So nothing would change there. Vertical, yeah, we'd still have these, right? How about the horizontal? Yeah, this is case 1. Because now the degree of the numerator is 3, degree of denominator is 2, the top's bigger than the bottom, you have none. So how would that change our picture? Well, just so you know, we wouldn't have any dotted lines to flatten out to. So the inside would still look like this. Wait a minute. Hold on, I have to think this one through. 1. Yeah, negative. Over there, -1, negative. Should be positive. And then on this side, 3, yeah. So, you know on this side, on the last one, it went up like this, and on over here, it flattened out, right? This time, it doesn't flatten out. It actually turns back up and heads off to infinity like this. And on this side, it does the same thing. It kind of goes like this. Then over here, it does not flatten out, turns back and heads down to negative infinity like that. But again, we're not going through the graphing of these, all right? So you feel if I gave you something reasonable here that you could do this, set the bottom to 0, compare the degrees, case 1, 2, or 3, and yeah?
So we face the dots. It's going to be those 2 lines, right?
These dotted ones, the vertical ones, and then the horizontal ones. If there are any. If there aren't any horizontals, you'll just say there's none.
Right,
For this specific example, there's none. Yeah. Okay, now, I'm going to give you a word problem. And this is going to seem like it's kind of coming out of nowhere, but I've got to do something similar to what's on the homework. All right. So first, let me give you the function. S of P equals 90 over 100 minus P. All right, let me read you the problem because I don't want to write all of this down. Heavy metal contaminants in a cement quarry may be removed from the soil by planting sunflowers. I didn't know that. So you have this quarry, you have contaminants, heavy metal contaminants that have soaked into the soil. You can actually remove them by planting sunflowers. Sunflowers, I guess, absorb the heavy metals and convert them into something, and so you can remove them by planting sunflowers. Use the following model to estimate the number of sunflowers measured in thousands needed to remove P% of contamination. Okay, so P in this problem is equal to the percent contamination removed. As an example, 25% we would write as 25. Let me make sure I have that right. Yeah. 25% would mean P is 25. S in this problem is equal to the number of sunflowers measured in thousands. All right. Let's see. Do y'all understand the problem, the way I read it? You have this contaminants in the soil. Okay, this is the model we're going to use. If we want to remove P% of the contaminants, then we're going to plug that P into that formula, and it's going to tell us how many sunflowers we'll need. Let's just look at one particular example. I haven't asked the question, have I? I have not asked the question. I just want to make sure we understand the function. What if I wanted to remove, how many sunflowers would it take needed to remove 10% of the contaminants? So what would I do to answer this question? Plug it in for P, right? 10. We're going to do S of 10, right? That's what we're going to do. Plug 10 into that. And what would that give you? 90 over 100 minus 10, which is 90 over 90, which is 1. So we're going to just plant one sunflower, right? No, 1,000. Remember, this is measured in thousands, right? Understand? So that means the answer to this question is 1,000 sunflowers. So it's this times 1,000 is our final answer. Does that make sense? Yeah. Okay. So if we want to remove 10% of the contaminants from the soil, we're going to have to plant 1,000 sunflowers to do that. Now, the thing about problems like this is it's actually impossible to remove all of the contaminants. There's not a way to do it. And our function should somehow tell us that. So let's try and get some more out. How much do you want to try and get out this time? 10%? Let's go up a little more. 50%. Okay, what about if we wanted 50%? Well, then we'd have to plug 50 into this. And that'd become 90 over 100 minus 50, which is 90 over 40, right? No, I can't do. What the heck? That's wrong. That okay? All right, so what is that? So as a decimal, what is this? 1.8. So multiply that by 1,000, we have to put 1,800 sunflowers. Right? 1,800? With me? All right, so look, I mean, to get 10% out, we did 1,000. To get 50% out, we only need 1,800. So what, maybe like 4,000, we should be able to get it all? Maybe? All right, let's try and get 90% out. Let's try and get 90% of the contaminants out. Okay, 90%. So what happens now if we try and plug in 90 over 100 minus 90? That's 90 over 10, which is 9. So now, oh wow, what have we jumped up to now? 9,000. Does that make sense? What's happening? Look at this function now. Look at this function now and look at it in the sense of what we were just doing in this class. This function is a rational function, isn't it? And it has a vertical asymptote where? Where does this have a vertical asymptote? At 100, doesn't it? So if I were to look at this graphically, at 100, I have this happening, don't I? And this is the number, this is giving us the number of sunflowers I need. So, you know, we said at 10%, right? At 10%, we only needed 1,000 sunflowers. Let's say that's 1,000. At 50%, I needed like 1,800, right? But what's happening at 90%? It's shooting straight up, isn't it? This thing's starting to go like this. Do y'all see that? Can we get 100% out? No, because if you plug 100 in here, you get division by 0, and it can't happen. So could we try for 99%? Sure. But if we plug 99 in here, I'll let you do it yourself. If you plug 99 in here, you're going to get, I believe, 90,000 sunflowers. It just becomes impossible. It's just impossible for us to remove everything from the soil. So we need a model that represents that kind of limit of how far we can go. Does that make sense? Okay. All right, so here's what I'd like for you to do for your homework for this. Let me just double check the homework on this page. Okay, for your homework, I don't even know if I have the right page or not. Just do the first 8 problems for rational functions. Do you have yours right there? Yeah, let me see. That is, yep. That's on page 88. Do the first 8. That's pretty easy to remember. On page 88, do the first 8 problems for your homework. All right? So the first ones, the first 6 of them, they ask you to find the vertical asymptotes and the domain. That's what they ask for. Just do what we did in class. Find the vertical asymptotes and horizontal asymptotes for the first 6 problems. All right? And then the next 2 are word problems. I want you to kind of mess with those and see how they go. All right? Any questions? Okay. That's it. Let's call it a day. I think, don't want to start a new topic. Whoa, excuse me.